Algebra 2, Chapter 13.2, exercises 23 through 26. This is the section where we continue to work on exponential growth functions. And we're going to start out with practical applications of exponential growth functions. The population of a small town is 15,000. The population is growing by 5% per year. How long will it take for the population to reach 25,000? The basic form for this is you're going to have a function in terms of time, which we'll call f of t. And that's going to be equal to our starting amount times 1 plus r to the power of t. So in this case, we've talked about initial value, base. Well, our base in this case is equal to 1 plus our rate, which is r. And here we're given r is 5%. Well, r equals 5%. And that's a certain way of saying a number, but 5% is equal to 0.05. So our function here is going to end up being f of t equals our starting value, which is 15,000, times our base. Well, in this case, our base is 1 plus 0.05, which equals 1.05. So we have our base of 1.05 to the power of t. Now, for population growth and monetary growth, these equations are very similar. And so we can go to our calculator, and previously I entered this function in the calculator, and we're trying to see how long it takes. Well, when we graph this in the standard window, we just don't see anything. And the reason we don't is because our starting value is 15,000. And so we're going to change our window. And for my window, I'm going to go to my x value, my y value, we can start at -10. But we know we need to go up to 25,000 because that's what we're trying to find. So I'll put here 25,000 as our y max, and we're going to scale at 1,000 people. So we're going to see that. And as far as time, I don't have a good idea of how much time it's going to take. I know we're going to start at year 0 because that's the only one that matters. And I'm just going to say 20, as in 20 years. Okay, so our x scale is time. And time is usually on your independent variable axis. And now when we graph this function, we should be able to see, I hope, yeah, so we see the thing starting out at 15, going up to, we had window, y max 25,000. I want to go to 30,000 because I want to go beyond where we are. So we graph this right here. And now we really have some choices to deal with. We can see that the graph of this function is going to match. Now, it looks, you can see it's slightly curved, but it's sort of close to linear. You look up at a graph of any curve closely enough, it looks like a line. Anyway, let's go to trace again. For x equals 10, as in 10 years, we get 24,000 people. And so we can continue to go up. And right here, at 10.45 years, we're getting very close. So about maybe 10.5 if we round to the nearest tenth of a year. But we can get a more exact value if we go to our y equals, our function editor, and put in 25,000 here, and then graph both equations at the same time. And this intersection point, which our calculator will determine, will give us an even more exact answer. So we go to second, trace, 5, enter, enter, enter. So we get 10.46 years. So we'll call this 10.5 years. How long will it take? T equals about 10.5 years. So anyway, that's it. We'll go on to the next other problem, which is 25. Analyze relationships, compare the behavior of g of x equals 2 to the x power and f of x equals x squared. And I've thought of these a lot because it's just, you have 2 to the power of x and x to the power of 2. So what do they look like? And really, I'm going to just put these quickly in the calculator, go back here and put in 2 to the power of x and x to the power of 2, and press zoom 6 to get a standard window, and we see these functions right here. You look to the right, here in quadrant 1, they don't look that far apart. Anyway, let's go ahead and just compare and contrast what it is. G of x, for g of x equals 2 to the power of x, our domain is going to be all real numbers, and our range is going to be, we don't actually touch the x-axis, so we're greater than 0, less than infinity. That's our domain and range. The in behavior, so limit as x, well, we write it in this class as g of x approaches infinity, as x approaches infinity is the way we put it. As x approaches infinity, g of x approaches infinity. Okay, also as g of x approaches negative infinity, x approaches negative infinity, what does g of x approach? Let's look at our graph again in the calculator. It's this blue one here. What are we approaching as we go to the left toward negative infinity? 0. So, and then for, I'm going to use the red here, for f of x is equal x to x squared, and then for our domain, we have the same domain. It's a polynomial function. We have greater than negative infinity, less than infinity. We have our range. Now, is our range going to be the same? Well, no, it is not. And the reason it's not is because we actually do, the range does start at 0, and then goes up to less than infinity. And then, I'm going to try to skip a skinnier pen here. Okay, as x approaches infinity, f of x approaches infinity. As x approaches negative infinity, f of x approaches also infinity. And then there's one other, so these are just some comparisons. There's also both f of x, f of x, and g of x are what we call bounded below. So that's one thing they have in common. So there are some things. There might be some other things about this, but these are the main things I'm looking at here. Okay, 26, you explain the error. So there's an analysis done, and so you can explain that. And then the last thing we're going to go over is what we call the lesson performance task, which is really pretty much like problem 23 we did at the beginning of the video lesson. Like all collectibles, the price of an item is determined by what the buyer is willing to pay and the seller is willing to accept. The estimated value of a 1948 Tucker 48 automobile in excellent condition has risen at approximately exponential rate from about $500,000 in December 2006 to about $1.4 million in September 2013. So find an equation in the form v of t equals v sub 0 times 1 plus r to the power of t, where v sub 0 is the value of card dollars in 2006. And so so it's the starting value is this v sub 0, and then r is the average annual growth rate. T is the time in years since December 2006. Okay, so and then it says hence substitute the known values and solve for r. So what I'm going to do is take this problem here and shrink it just to leave more room to work to the right here. And if we view it again, we need to. Okay. So here we are again. All right. So find an equation. I'm going to work an equation to the right. We're going to have v sub t. That's going to be our final value. Will be 1.4, and I'll put the total value here equals v sub 0, which is 500,000 times 1 plus r to the power of t. Well, t is going to be, let's see, t is the time in years. So we're going to go from December 2006 to December 2013. So what we have is 2013 minus 2006. That's going to be our value t, which is going to be 7. So 7 goes in the place of t here. So now we can go about solving. Now we're just going to solve for r, and we're going to have our answers. But this is our answer to, we'll find an equation and substitute and solve for t. Okay, so we're still on part A. What we're going to do is divide by 500,000. Now, one thing you can do in these problems that can really make things easier for you, instead of going by years, you can go by millions of years, or years, I mean dollars. So I can put here, instead of 1,400,000, I can put 1.4 equals 0.5. And 500,000 is 0.5 million. So now we can just, it just makes the arithmetic a little easier. Divide by 0.5. And dividing by 0.5 is the same as multiplying by 2. So we have 2.8 is equal to 1 plus r to the power of 7. Now what we're going to do to continue to solve for r, what we're going to do is take we can cancel this out by taking the 7th root. So all I'm going to do is move this, I'm going to put this 1 plus r over here to the power of 7. And that's on the left side. On the right side, I have 2.8. And what we're going to do is take the 7th root, which looks like this, and put 7th here, and the 7th root on the other side. And so what you have is the 7th root and the 7th power cancel each other. So we're left with 1 plus r is equal to the 7th root of 2.8. And then we have r. We can subtract 1 from both sides of this equation. R is equal to 7th root of 2.8 minus 1. So let's go ahead and do that in the calculator. Quit. R is equal to the 7th root of 2.8. So to get that, we can go to math, and we can go down to this option 5, where we can use different roots. So we go here, and we can put the 7th root here of 2.8, and from that we subtract 1. So we're going to get 0.158, which, to get into a percentage, which is what they're going to look for, what we have to do to this, we have to multiply by 100. So we say 15.8, we'll call it 15.85%. So R equals 15.85. Put 0.1585. Which is equal to 15.85%. And that's going to be solving for R. Okay, so we'll just call this our answer choice, our answer to part A. What is the meaning of the value of R? Well, it's going to be the percentage. This will be the percentage growth rate. Percentage growth rate. So that's our answer to part B. And finally, for part C, if this trend continues, what would be the value of the car in December of 2017? Well, for this, T is going to be equal to 2017 minus 2006 is to 11 years. So what we have here is f of t, and t is 11, which is going to be our answer, is going to be 0.5, or we can call it 0.5 times 1.15. Remember, it's 1, the base is 1 plus r, 1.1585 to the power of 11. So let's go ahead and do that. So, calculator, 0.5 times 1.1585, and that's slightly rounded, of course, so it'll be a little bit off the power of 11, and so we're going to get $2.52 million. Put 2.52. So we say the trend, we say the car will be worth about $2.52 million. There we go, $2.52 million. So anyway, that's going to be it. And this is it. Good luck on all the other problems. I hope this can help to you. And as always, thanks for viewing.